Hello everyone, welcome back to part 9 of Shallow Foundation series. In the part 8 we had seen how to conduct a plate load test in order to determine the bearing capacity and settlement of the soil. So in this part we are going to see how to utilize that data of plate load test in order to determine that bearing capacity of soil that we have talked about in previous video. So if you have not seen that video, please go and check out that video. Until and unless you have seen that video, this video tutorial won't make any sense. So I'll give you the link somewhere at the top. Please go click on that video first, then you can come back here and watch this video. Okay, so this is a particular load versus settlement curve that comes after when you perform a plate load test on a soil. So using that curve we can determine the bearing capacity. Okay, so we'll understand this curve, how to draw it and how to determine bearing capacity by using a small numerical. This is a statement of numerical given over here. A plate load test was conducted on a uniform deposit of sand. It is very important that the given soil is a sand and the following data were obtained. So what we have obtained? We have obtained pressure in kilonewton per meter square and the settlement. This is what we do in plate load test. We determine settlement against the pressure. So this is what the data is given. The size of the plate was basically it was a square plate of 750 mm by 750 mm and the pit size was 3.75 meter by 1.5 meters. What we have to do, we have to plot the pressure versus settlement curve and determine the failure stress. This is what we have to do in part 1. In part 2, what we are going to do is if a square footing of size 2 meter by 2 meter is to be founded at a depth of 1.5 meter in the soil, assuming the factor of safety of 3, we have to determine allowable bearing pressure, or you can also determine the safe bearing capacity. This is what we have to do. We have to do two parts. In part 1, we'll draw pressure versus settlement curve. In part 2, we'll use that data from pressure versus settlement curve in order to determine safe bearing capacity of the soil. Okay, so in part 1 we are going to do this. Okay, so on x-axis, this is usually the convention that we use. On x-axis we keep the pressure, and on y-axis we keep the settlement. So you have the pressure data, you have the settlement data. Just keep on plotting this point. First point will be 50 and 1.5. That point will come, let's say, somewhere over here, like this. Over here that point will come. Second point 100 and 204, 300 and 7.5. So you just keep on drawing these point and just join them all by a smooth curve, and you will get a load versus settlement curve like this. One thing that you will notice, this is very important over here, that this curve does not start from zero, that is zero pressure versus zero settlement. So what we have to do, we have to draw the curve little bit in backward direction like this. This procedure is called as applying the zero correction. Okay, so you draw the curve, a smooth curve using the load versus settlement curve from plate load test, then you apply the correction zero correction, and then once you are done that, what you will do is you will draw two tangents. One tangent which goes like this to the first straight part, because this curve has a two straight part. First straight part of the curve is at the start in this region, other one is after the failure. You also get a second straight part. So what we do is we draw the tangent, or we extend the straight portion from the start as well as from the end like this, and wherever these two lines meet, these two tangents, wherever these two tangents meet, that point is nothing but your failure stress. So in this case, for this soil which is given to us, the failure stress is about 500 kilonewton per meter square. Okay, second, this failure stress is nothing but equals to the bearing capacity of the plate. For that plate, remember, it is not for the this plate load test we conduct onto the plate. That's why the failure stress is of the plate, and this Q ultimate that you have got is also for the plate, not for the function. Remember, this is very important. So as for our definition, how do we define bearing capacity or ultimate bearing capacity? It is the maximum pressure where your soil fails in shear. That is why your failure stress becomes your ultimate bearing capacity. Okay. Similarly, you can determine the failure settlement at the failure point. You just have to draw a line like this. This is it, will go somewhere around 10, 11 or 9.5, something like that. So I have just written delta, that is settlement at the failure point, equals to approximately 11 mm, or it could be 10 mm. It's not very accurate curve. Okay, so this is how we determine failure pressure and ultimate bearing capacity of the plate by using plate load test. This is where your part 1 of the numerical ends. In part 2 of the numerical, okay, before I go to part 2, I just want to clarify one more method, because this is just a one method of determining the bearing capacity or a failure stress. But this method is little bit difficult. There are a lot of possibility of you making an error. So there is an improvised method of doing this entire procedure of determining failure point. That improvised method is called as Abbott's method of improvised plotting. This method is also recommended by Indian Code IS 18888 1971. In this method, what we do is, instead of plotting your load versus settlement curve onto the normal graph, we take a semi-log paper. It's not a semi-log paper because semi-log paper has a logarithmic scale on only one direction, but over here you can see logarithmic scale is on both directions. So what we do, instead of plotting the load versus settlement curve onto a normal graph paper, we plot it onto the log graph paper. So because of that, what happened, when you plot this curve onto the log paper, you will see two different straight lines. So part 1 is here, first straight line is here, second straight line you will get over here. Wherever these two lines intersect is nothing but your failure pressure. Okay, this is like this, and this is your failure settlement. So this graph is not for our numerical. I have just taken it from a book, but this is how you can do the very accurate analysis of failure point. Okay, so this kind of analysis is basically used for a soil which does not show distinctive failure pattern, because if you go back to my previous video, you will see there are 3 different curves of load versus settlement curve. In curve 1 and 3 you see this kind of curve, and in curve 2 you have to go back and refer that video unless and until you would understand. So for that part we can use this method. Okay, I think I have created a lot of confusion here. So in general, what we do is this method that you have seen over here, drawing the tangent, we basically use for a soil which is very hard and stiff in nature. That is, this method is good for that kind of soil. If your soil is a clay soil or a normally consolidated clay or a loose sand, you have to use Abbott's method. Okay, this is what you should remember. Anyways, let's go ahead. So this is where our part 1 ends. We have determined the failure stress and ultimate bearing capacity of the plate. In part 2, what is being asked to us, if a square footing of 2 meter by 2 meter is founded onto the same soil, what will be its bearing capacity if you consider a shear failure factor of 3? Okay, this is what we have to do in part 2. Now, what is our solution strategy for this part? We'll apply Terzaghis bearing capacity equation to the plate at first. Okay, then after that, by using this Terzaghis equation, we will determine the bearing capacity factors for the given soil. Okay, this is what we will do for the plate. And the bearing capacity factor that we determine for the plate or for that particular soil, it will be same for the foundation as well as the plate. Okay, this is why we need to determine bearing capacity factor. Once we determine bearing capacity factor, we can apply Terzagh's equation to the soil, to the foundation. Okay, so in step 1 we'll apply the Terzagh's equation to the plate. In step 2 we'll apply the Terzagh's equation to the footing and we'll determine the bearing capacity of soil. Okay, so let's see the step number 1. This is what the Terzagh's equation look like. We are applying it to the plate. Okay, so CNC plus gamma df nq plus half gamma b n gamma. And as at the start of the video I told you that this is a sand, so that means the value of C is 0, so this factor get cancelled. Other thing is, if you can look at the arrangement of plate load test, you will see that this is your plate and there is no surcharge pressure here. Okay, the plate is not there is no soil above the plate. That means your surcharge, this factor also becomes 0. Why it becomes 0? Because your df is 0. df comes when there is some soil present above your foundation, but over here there is no soil present above your foundation. That's why df is 0. That means your q ultimate is equals to this value, half gamma b into n gamma, and here b is nothing but b is the width and that is nothing but the width of the plate. So your equation for q ultimate for plate becomes half gamma b of plate and n gamma. That is what you have to remember over here. Okay, so what we are doing, we are applying the Terzagh's equation to the plate and trying to determine bearing capacity factors. So if you look at the numerical, you will only need to determine this n gamma. Okay, so how we can do it? So this is your equation. The width of the plate is given to us 750 mm, that is 0.75 meters. Gamma is not given in this numerical, so I have just assumed randomly gamma is 20 kilonewton per meter cube. And q ultimate, this q ultimate is for the plate and this comes from the curve. Okay, we have seen q ultimate equals to nothing but the failure stress. The failure stress was 500, so your q ultimate is 500. So we'll equate this q ultimate from the graph with the q ultimate equation of q ultimate for Terzagh's bearing capacity equation. Once you equate these two values, you will get the n gamma is 66.67. As it is a bearing capacity factor, it will not have any unit. So this is how we determine our first bearing capacity factor, n gamma. And by using this Terzagh's bearing capacity factor table, we can also determine nq and nc. But I will not determine the value of nc. Why I will not determine the value of nc? Because nc comes into the picture when your value of c is given. But this is a sand, so we don't need, because c is 0, so we don't need the value of nc for our footing. So I'll not determine the value of nc, I'll only determine the value of nq. In order to determine the value of nq, what I have to do is I have to also determine the value of phi by using this table. Now how I am doing this? I am doing it by interpolating the values of phi. Basically what is happening over here, the value of n gamma 66.67 is somewhere, let's say over here. It is between phi equals to 35 and phi equals to 40. So these are the two values of phi, and our n gamma equals to 66.67 lies between these two values. Okay, so this is your equation of linear interpolation which is given over here. Use that equation and determine the value of phi equals to 37 degrees. That value comes as a 37 degrees. So there is one very big assumption that I am doing over here, that you guys already know how to do the linear interpolation and you can determine this value by using the equation which I have given over here. If you guys have any trouble in doing this linear interpolation, please let me know. Maybe I'll upload a PDF of explaining this procedure in entire. Just let me know into the comment or text me my number, whatever. So what we have done over here, in order to determine the value of NQ, I have determined the value of phi corresponding to this n gamma equals to 66.67. Now if you can see into this table, this phi equals to 37 degrees is again not available. So what we have to do, we have to again interpolate the value of NQs in order to determine NQ related with 37 degrees. So once you do that interpolation, you will get the value of NQ as a 50.96. Okay, so please do the interpolation. If you don't understand it, just let me know. I'll upload a PDF explaining this entire procedure. Okay, so what we have got, our objective in part 1 was to apply the bearing capacity equation to the plate and determine the values of bearing capacity factor. So we have determined these two factors, n gamma and NQ. Now we can apply this Terzagh's equation to the footing. Okay, so this is our equation. Now if we look at the equation, instead of taking 1/2 or 0.5, I have taken it as a 0.4. Why 0.4? Because Terzagh's equation are different for different shape of the footing. So the first equation, the general equation, is applicable for the strip footing. Then you have a circular footing, then you have a rectangular footing, and then you have a square footing. The given footing to us into the numerical is a square footing. That's why into the square footing equation you need to add 0.4 instead of 1/2. Okay, next C is 0 as usual. So this is what your equation of Q ultimate becomes. Now in this equation we already determined NQ, N gamma. We know the gamma equals to 20, DF is given 1.5. Okay, and this width of the footing is 2 meter. This is what all I have given over here. Just put the values into the equation and you will get the Q ultimate as this value. Okay, 2595.52 kilonewton per meter square. This is how you determine ultimate bearing capacity. But our numerical does not end over here. Why? Because we don't have to determine the ultimate bearing capacity. We have to actually determine allowable bearing pressure or safe bearing capacity. So just do one thing, go and refer part 1 of shallow foundation if you want to understand what I am going to do next. Because from Q ultimate to safe bearing capacity, there are 4 or 5 definition. You must know all this definition in order to understand the next step. Okay, so from the Q ultimate we'll calculate net ultimate bearing capacity. Net ultimate bearing capacity is nothing but this Q ultimate minus the surcharge pressure, which is nothing but gamma into DF. This is what I have done. This Q ultimate is here. We have determined this is the value of gamma, this is the value of DF, and this is called as surcharge value. Once you subtract that value, you will get your net ultimate value. Again, this is not our final answer. We have to determine safe bearing capacity. So we'll keep going on ahead. So from net ultimate bearing capacity, we can determine net safe bearing capacity. This is the equation. Net ultimate, we are just determined into the previous step. Factor of safety, FOS is given 3. If it is not given, you can assume any value between 2 to 3. Okay, so just do the calculation. You will get the net safe bearing capacity. Now you can stop your numerical over here, because this is what nothing but the allowable bearing pressure. But if you want to determine the net, not the net safe bearing, if you want to determine, you can stop it here, or you can go 2 more steps ahead and determine the safe bearing capacity. How we determine safe bearing capacity from net bearing capacity? Net safe bearing capacity is this. Just add the value of gamma DF into your net safe bearing capacity and you will get the Q safe. Okay, so I have just added gamma into DF into the equation, and this is the value of Q safe. Okay, so this is how you can determine bearing capacity using the plate load test. Okay, I hope you understand so far what I have taught in shallow foundation series. This is where I am going to end this series. From next video tutorial onward, I'll be teaching probably pile foundation. Okay, so you can just go into the description section and download the PDF for this solution, or this solution will also be available into your Google Classroom. You guys take care. This is where your numerical ends.